An ordinary differential equation is an equation that contains only one independent variable and one or more of its derivatives with respect to the variable. For example, we have y prime, etc. with respect to x. And there are different types of ODEs. First of all, we have the autonomous ODE, where the independent variable does not appear in it. For example, y prime plus omega squared y equals 0. So here we don't see x anywhere, which is an independent variable, or t. And then secondly, we have the linear ODE. A linear ODE can be written as the linear combinations of the derivatives of y. And we have two types of linear ODEs. First of all, we have homogeneous linear ODE. It can be written in the form y prime plus p of x y prime plus q of x times y equals 0. And then the non-homogeneous linear ODE, it can be written as y prime plus p of x y prime plus q of x y equals f of x. So the difference here is that 0 appears in the homogeneous linear ODE, but instead of that 0, we have a function of x in the non-homogeneous linear ODE. And then the third type of ODE is nonlinear ODE, which contains nonlinear function. So for example, here we have y prime equals y squared. So y squared here is nonlinear. That's why the equation is a nonlinear ODE. Secondly, we have partial differential equations. So a partial differential equation is a differential equation containing partial derivatives of the dependent variable, one or more dependent variables, with more than one independent variable. So it can be written in the form right here. It's a function of the independent variable x1 till xn, depending on the number of independent variables, and then function u, and then partial derivative of u with respect to the one or more independent variables. And then there are different types of partial differential equations. There's the first order PDE, which is an equation that has only the first derivative of the unknown function having m variables, and it can be expressed in the form of f of x1 to xm depending on the number of independent variables, and the function u, and then partial derivative of u respect to one independent variable. For example, we have partial derivative of z with respect to x plus partial derivative of y with respect to x is equal to x plus zy. And then there is the quasi-linear partial differential equation, in which the terms with the highest order derivatives of dependent variables occur linearly. For example, we have x times partial derivative of u with respect to y plus y times partial derivative of u with respect to y is equal to x squared plus y squared. We can see that the partial derivatives here, u with respect to x and u with respect to y, occur linearly because x and y here are the coefficients. And then we have homogeneous and non-homogeneous partial differential equations. So homogeneous differential equations is an equation where all terms contain the independent variable or its partial derivatives. Otherwise, it's called non-homogeneous. In the example, we have second partial derivative of u with respect to x, and second derivative of u with respect to x and y squared, and then plus second partial derivative of u with respect to y is equal to x squared plus y squared. So here the terms x squared plus y squared do not contain the partial derivative of the dependent variable or the dependent variable itself, which is u. So it is a non-homogeneous partial differential equation. And now moving on to the solvers. How can we solve differential equations? So first of all, we have the Euler's method, which is very common because it's very simple to implement. So Euler's method solves the equation of the form y prime equals f of x and y with the initial condition y of x0 equal y0. So from this method, we can So this method comes from the fact that the tangent line at xi and y of xi approximates to xi and xi plus 1. And then from that we obtain the formula yi plus 1 equal y of xi plus h f of xi and y of xi. So it's pretty simple. So it's basically just applying the formula and plugging numbers in there. So for example, we have the differential equations y prime plus 2y equals x to the x cubed times exponential of negative 2x. So we're trying to write the equation in the form y prime equal f of xy. So we have y prime equals negative 2y plus x cubed times exponential of negative 2x. So x0 is going to be equal to 0 and y0 equal to 0. Then by applying the formula with h equals 0.1, we need to find y for x equals 0.2. So we have y1 equals 0.8 and y2 equals 0.64. So that's the value of y at x equals 0.2. And then we have the predictive Euler's method, which is based on the Euler's method, but there is a correction applied to it. So from the Euler's method, we have yt1 plus t plus 1p equals yt plus h f of xt and yt. And then by applying the correction method, we have yt plus 1c equals yt plus h times f of xt yt, which has been calculated before, plus f of xt plus 1 and yt plus 1p. Yt plus 1p is basically what we got from step 1 and the whole thing divided by 2. And then we have the Runge-Kutta-4 method, which is more accurate than the Euler's method because it has a lot of intermediate steps in it. So this is the formula right here. Yn plus 1 equal yn plus 1/6 of variable k1 plus 2 times k2 plus 2 times k3 plus k4. And then we can see here the formulas for the variables k's are all here. And one thing to note is that it solves the equation under the same form as the Euler's method, which is y prime equal f of xy. And now we're gonna move on to the control system. So a first order control system is a system where the relationship between input and output, which is transfer function, involves the first order derivative. So here we have the general form b0 over s plus a0. If the input function is a unit step, then we have the time-based function, which is b0 over a0 times t minus b0 over a0 times exponential of negative a0 times t with t greater or equal than 0. So first of all, if the coefficient a0 is greater than 0, then exponential of negative a0 times t will tend to be 0 as t approaches infinity. That means that the system is stable. But second case, if a0 is less than 0, then exponential of negative a0 times t will approach infinity. As t approaches infinity, then the system will be unstable. Then we have the second order, and the transfer function has the general form omega n squared divided by s squared plus 2 times zeta damping coefficient times omega n plus omega n squared. And we have different cases. So first case, when the system is under damped, that means that that zeta, the damping coefficient, is in between 0 and 1, the system oscillates. And second case, when zeta is equal to 1, there is no oscillation, as well as when the zeta is greater than 1, there is no oscillation as well. And then different other cases, when we got complex poles, that means that there's gonna be oscillations and then an overshoot. And then when the damping ratio increases, there's gonna be less oscillations, and then the omega n increases, then oscillations die out faster. And then the third order is in this form, which is g of s equals k over s plus b times s squared plus 2 omega n zeta s plus omega n squared. So here s squared plus 2 omega n times zeta s plus omega n squared is characteristic of the second order transfer function. So this case is going to be very similar to second order transfer function. When the damping ratio increases, then there's going to be less oscillations, and when omega n increases, oscillations die out faster. So now moving on to the history of uncertainty. So in 1963, Horowitz showed how to design uncertainty-tolerant controllers using classical root locus and frequency response methods for plant models with several uncertain parameters. And then in 1967, there was the application of linear quadratic game theory. So the game theory has been applied to design uncertainty-tolerant controls laws. And then in 1975, there was a lot of groundwork for emergent theory of multivariable stability margin, which was the groundwork for robust control theory. And then in 1978, there has been the emergence of Lyapunov conic section positivity and small gain anticipativeness for stability theories. And then between 1980 and 1982, some variables have been introduced, so Km and mu notation. So Km is the excess stability margin, and mu is the reciprocal of Km. And then 1980 has been the robustness revolution spread to adaptive control. That means that it's been proved that adaptive control algorithms had small robustness, and robustness has been since applied to adaptive control. And then in 1988, there's been a big innovation in MATLAB. MATLAB introduced the robust control toolbox, which allowed the robust control design to be widely accessible to students and engineers. And in 1992, there's been the crash of the YF-22 Raptor, which was designed with robust controllers, which means that the field of robust control is not perfect, and there is still a lot of improvements, room for a lot of improvements, and a lot of improvements need to be made till today. So here we have an overview of optimization. What is optimization? Optimization, the goal of optimization is to find a function that maximizes a certain functional problem. That means an infinite dimensional optimization problem. So there are two types of optimization. There is static optimization, where the variables of the system does not change over time, and there is dynamic optimization, where the variables of the system change over time. And in order to solve an optimization problem, we need the mathematical description of the model. That means a differential equation that describes the problem. And then we need the specification of the performance index. And then we need boundary conditions. And we have a diagram that describes the tools that need to be used for an optimization problem. So there is geometric approach and algebraic approach. So for single stage deterministic single interest algebraic approach optimization problem, we're gonna use calculus and Lagrange multipliers, linear and nonlinear programming, calculus of variations, and functional analysis. And for multiple stage, the tools that need to be used is dynamic programming. So one thing to note about optimization problems and history is that in the 1970s, interest in control theory shifted from optimality to robustness because of failures of optimal control theory in multivariable feedback methods. So there's been some interest in robust control theory.